video, we're going to talk about pointer analysis, aka alias analysis. As the name implies, this is going to be about analyzing programs that use pointers. To motivate why we care about pointers and about loads and stores to memory, I want to, at the risk of overstating a point, show that lots of languages, in fact almost every programming language you've ever used, has pointers. It's maybe really obvious in C because things are manifestly pointers all over the place. Every time you see a star, there's a pointer involved. Like, for example, in this innocent-looking implementation of a string copying-like function in C. Java also has pointers. You may not see stars quite as often in Java, but everything that's not a primitive type like int or bool is using a pointer under the hood. That is, everything that has a sort of ordinary object type or an array type, that's using an actual pointer. So when you do, for example, when we're doing this, writing this method that takes in an object, and we're doing a comparison using equals, that's doing a pointer comparison. OCaml has pointers all over the place, used implicitly. There's a whole bunch of times that OCaml programs use pointers that you're not even aware of. You can also explicitly use pointers, aka references in OCaml, using the ref thing, and then you do a exclamation point thing, which is the moral equivalent of a dereferencing star in C. In any case, there are definitely pointers that you can use and manage yourself in OCaml. So in general, pointers are really everywhere, and it makes sense to try to analyze programs and to try to optimize them in the presence of using pointers. Braille also has pointers if you use the memory extension. You've probably encountered the memory extension before. Maybe you've even written programs that use the memory extension, the instructions from the memory extension. There's an alloc instruction that creates for you a new location in memory. There are store instructions that you put values into memory. And there's a load that's not shown here, but there's also a pointer add that lets you sort of move around pointers in memory. There's also a free, also not shown here. But the important thing is that there are values of type pointer to something. So vals is not an integer itself, but it's sort of like a int star in C. That is, it's a pointer that can refer to an int. I'm going to give you a second to just read this program and refamiliarize yourself with how the Braille memory extension works by thinking about what this program does. I have another program to show you and to have you ponder. This program is written in something like C, and my question for you is what this program returns. Pause the video now and think about what this program does and what value it produces as a Boolean. The simple answer to this question is that this function always returns true. That is, it's easy to see that we are putting the letter A into the location pointed to by A, and then we're reading it back out of A without changing it again, and therefore it must still equal the value A. Therefore, this expression is going to return true, and the overall function is going to return true. That sounds great. Unfortunately, it is wrong. And the reason it's wrong is because, like everything else involving pointers, this program is made more complex in the presence of aliasing. That is, the possibility that the two different pointers may point to the same location in memory. If we're just talking about normal variables, like normal stacks locks, and this were just a normal assignment to a variable A, this were just a normal read from a variable A, then it would definitely be true that we could optimize this program to just say return true without actually doing anything else. But because there's pointers, because the pointer to the A pointer and the B pointer might actually point to the same location in memory, that may be the same memory address, when those two things point to the same location in memory, this function returns false, because we're storing a different value into the same location before reading it back. So an optimization we might like to do, that is eliminating this like hypothetically dead code, won't work in the presence of pointers, in particular in the presence of aliasing. And that's what this lesson is about. It's about deciding when two pointers can point to the same location in memory, that is, when they can alias each other. The reason that we're studying this is because it is truly essential to do anything at all with programs that involve pointers. Anything you might like to do, anything that seems easy or straightforward on normal programs without pointers, that is with normal sort of local variables that don't have the problem of aliasing, all of that is made hard or impossible if there's the chance that things might alias. That is, if we're dealing with pointers that are unrestricted. For example, we just saw an instance where we would like to eliminate a dead store, that is, a store to a pointer that doesn't seem to be used again, but it's not actually dead because of the possibility of aliasing. Some later read may read from the same pointer, so we can't eliminate something that looks like it should otherwise be useless. Similarly, this example involved an opportunity to propagate a store to memory through to a load and therefore get rid of both the store and the load. And that is made impossible because there's an intervening store to a completely different pointer that, if it aliases, kind of ruins the opportunity to do optimization. Similarly, you can imagine really pernicious cases where it seems obvious that you should be able to do loop invariant code motion, that is, to decide that some code is loop invariant, but because it uses pointers, you can't actually be sure that none of those pointers are being modified through other pointers that also are being used in the loop body. So you actually lose out a lot by not knowing that two things, by having the possibility that the two pointers might alias each other. An example that is close to my heart is that alias analysis is a major bottleneck on being able to automatically parallelize programs. If you wanted to, for example, take some code that is written in a sequential way and make it run on a vector machine or on a multi-core machine, you need to be sure that those code, those pieces, the code that you want to run in parallel with each other, that those pieces of code are independent. They can't interfere with each other. That is, when one writes, the other one doesn't need to subsequently read the value that one wrote. And that is often true if you know that the pointers involved can't possibly alias each other. But when aliasing is involved, you have to make conservative assumptions, and all your attempts at automatically parallelizing code are immediately ruined. So alias analysis is a really important analysis to do for all of these optimizations, basically to do anything with a code that involves pointers. So let's pose exactly what the alias analysis problem is. An alias analysis asks this kind of question. For every program point, that is every instruction, for example, in a Brill program, and for every pair of pointer-typed variables, that is anything that looks like pointer to something in Brill, can those two pointers point to the same location in memory at that point in time, that is, at that program point? There are several problems with this question, and the most fundamental one is that it's undecidable. That is, we'll run into halting problem-like issues if we attempt to always answer perfectly in the affirmative or the negative whether two pointers might alias. It's pretty easy to see, for example, how to reduce a alias analysis query that must say yes or no to the halting problem. That is, to have two pointers that alias if and only if another program halts. Therefore, we're going to have to do with approximations. And in general, even approximating this answer can be quite expensive. So the answer a lot of the time to the question, might these two things alias each other, will be sometimes. That is, I don't know for sure, but sometimes on some executions of the program they might alias each other and other times they might not. Finally, it's inherently an interprocedural question. That is, even simple functions like the string copying function I showed you earlier, the aliasing behavior depends on what our arguments are to the function. That is, whether we're called with pointers that alias each other or not. So in general, the way that alias analysis problems are set up is so that we can answer yes, no, or maybe. That is, we want to classify pairs of variables as either yes, these must alias, that is, in every execution of this program, these two pointers are exactly the same. They must not alias, that is, they can be any value, but they can never be identical to each other. Or we don't know, that is, that they might alias some of the time, but we don't have a definitive answer either way. And unfortunately, the awful reality of pointer analysis is that most answers to these questions are going to end up in this middle section. That is, most of the time, we won't be able to prove either that things never alias or that they always alias. The typical way that alias analyses are set up to benefit compiler optimizations is using may alias queries. May alias queries ask an analysis to say yes or no, where yes says that the two things might alias, but we don't know for sure, and no if we know beyond a shadow of a doubt that they must not alias. Optimizations can then use that information when the alias analysis is answered in the negative to do interesting optimizations. However, if the analysis answers yes, then we don't really know anything. We don't know if they will alias or not, and therefore optimizations are typically restrained. With that in mind, let's set up to do a may alias analysis in a straightforward way using the data flow framework. We will try to design a data flow analysis that tries to answer when two pointer values might alias the same location. So again, we will say no if we know for sure that they don't, and we'll say yes if maybe, that is, they might alias or they might not. I'm going to set up the first few fields in the data flow framework and leave it up to you to fill in the rest. This will be a forward analysis, that is, a normal one that goes from the entry block forward through the data flow graph. For the domain, I'm going to set it up so that we will have a mapping that goes from variables to memory locations of some kind. So the thing that we'll compute on the entry and exit of every basic block will be a mapping from variable names in the program to sets of locations that those variables might refer to. The idea is that then we can answer may-alias queries by doing set intersection. That is, if you ask me, might x and y alias at this point in the program, you'll look up this data structure for this point, for that point in the program, and then you'll get the associated sets for x and y, you'll get the set of locations. And if those sets intersect, then we'll say, yes, they might alias. And if that intersection is empty, then we'll say, no, they must not alias, and therefore you can do interesting optimizations. I'd like you to pause the video now and think about the rest of the aspects of the data flow framework. That is, what do we have to do? What will be the initial value for this analysis? What will be the merge function? And what will be the transfer function for these three instructions? You can think about how to extend these to all the rest of the instructions too, but these, I argue, are the important representative ones. Think about this for a moment and convince yourself that you have a minimal working, accurate alias analysis. We'll start out with an initial value that maps every single variable to the empty set. That is, variables don't refer to any locations, can't refer to any memory locations at all for the outset. So I'll just say for all x. The merge function will do a union at every variable. What I mean by this is that we're going to take the different mappings that we need to merge, at least two of them. We'll take all of the sets associated with every variable and pairwise take those sets and union them. That is, now when we're merging control flow, we now can say that the variable x can refer to any of the locations that came in from the left side or any of the locations that came from the right side. So that means that we'll union together all of those possibilities for every variable. For the transfer function, I ask you to think about these three functions, these three instructions rather, a constant, an ID that is a copy, and then an allocation. And the constant, you can think of this as being representative of other instructions also like add, because all we really need to do is in that mapping that we're producing for the output, we will just set that to the empty set. If we have x, if we were setting x to a constant, then we know it can't possibly refer to any memory locations. It's a constant like 5 or something like this. So it's not a pointer. And so we will set its associated set of memory locations to nothing. Then there's a copy. If we say x equals id y, all I want to do is set the output mapping for x to be all the same locations that we had for y. And finally, there's allocation. We now need to come up with a new memory location that represents this allocation. So we'll compute a fresh location, a fresh memory location, and say that the only thing that x can possibly refer to right now is that memory location. And this is kind of the key. This is where memory locations come from originally, is allocation sites. And then we'll be propagating them through the rest of the program using this data flow analysis. Let's now try to run this analysis on this tiny CFG I have on the slide. This program only ever uses one variable, two variables actually, x and y. So when we start out the program, x will map to the empty set and y will map to the empty set. Then after we do the transfer function on this first block, there's an allocation in there, which means that we have a memory, we need to associate a memory location with x. So in between here, we will have a mapping that still has, y go into the empty set, but x now maps to, let's just call this location 1. So x can only contain values from that location. After this, we'll have done our transfer that deals with copies with IDs, and now both x and y will map to the same location L1, to the set containing just one location L1. The next step is to analyze this block that just has a branch in it. Branches, of course, do not affect pointers, so we'll have the same value, that is a mapping from x and y, both to the set containing L1, going out of this branch and therefore back into the top of the loop again. We then need to run our merge function, that is our kind of pointwise union across these things, because we're merging control flow into the top of this basic block. So we will end up again with this mapping, that is x and y both mapping to L1, after we merge L1 with the empty set and then L1 with the empty set. now we have the same environment going into this basic block. So now my question to you is, what should we do with the transfer function that says that we need to come up with a fresh location for x to run this allocation again? How should this change the environment? I realize this is a somewhat philosophical question, but I would like you to pause the video and ponder for a second what we should do when we run the transfer function the second time for this block, now that it has a different in value. I think the most natural answer to this question is that we need to generate a new fresh location. That is, this is the second time conceptually around the loop, and therefore it's definitely going to be a separate location in memory that we're allocating here. Of course, the problem with this is that it doesn't converge. We will keep going around and around the loop, generating new memory locations and getting back to the top of the loop and ending up with a different input value. So we'll need to rerun the analysis for the loop again, coming up with a new memory location every single time, and this will run forever and never converge. By coming up with a new memory location on every analysis of this basic block, we have painted ourselves into a corner where we're kind of like actually running the program and coming up with a new memory location every time that we run the loop. And that simply won't do for an actual static analysis. I contend that the only reasonable thing to do instead is to associate a single memory location with every static allocation site. That is, when we analyze this basic block again, we won't come up with a new location L2, we will put the same old memory location L1 and associate it with the variable x. This seems a little bit odd because we know when we run the same loop twice and we allocate twice, we're not getting the same memory location. But what's going on here is we need to abstract away from that actual execution of programs with a model, with a static over-approximation of how memory actually works. So this gets us into the very important topic of heap models. Heap models basically answer the question, what is a memory location? If we answer this question with a memory location is an actual concrete pointer, that is an actual number that points to a location in memory, then we're going to end up with the non-termination and over-precision problems that we just saw when we tried to come up with new memory locations in every trip through the loop. So we need kind of an abstraction of memory that lets us do alias analysis in a computable and tractable way. The most straightforward heap model I can think of, and also a really effective one, is to associate every allocation instruction in your program with a single memory location. So this will be associated forever and for all time before we even start doing our data flow analysis with the location L1. We'll just label that instruction with that location in memory. So this means that our abstraction of memory is that, yes, there's a whole bunch of actual pointers when the program runs, but we're going to group together all those pointers that are allocated from this allocation site and call those all location 1 in our abstract domain of pointers. This frees us from the need to track actual pointers and gives us the tractability we need to solve the alias analysis problem. This, of course, has an impact on the precision of the analysis. It means that when we have two different pointers that come from the same allocation site at runtime, when we do our analysis, we will consider those to be the same location in memory. This seems obviously incorrect. Those are not the same location in memory, but all it is for the purpose of our analysis is conservative. Because we're doing a may alias analysis, all this can do is cause us to answer more of the time that yes, these two things might alias, which remember is the disappointing and useless answer. It's always safe to answer, yes, these two things might alias, because we're not going to use that to do any interesting optimizations. It is only unsafe, potentially unsafe, to answer no. That is, we can't answer the two things must not alias when there is some chance that they might. So this abstraction of the memory domain makes us conservative in the sense that we will be giving less useful answers from our alias analysis. On the other hand, it makes it possible to do the analysis, so that's a pretty good trade-off. This simple heap model works for Brill. For realistic programming languages, you inevitably want to make this slightly more precise at least. For example, in languages with arrays, you really want to have a separate memory location for every offset in the array often. And typically you want to have separate memory locations for different fields within an object if you're in an object-oriented language. The final aspect I want to talk to you about is bringing context sensitivity to alias analysis. We talked about the general concept of context sensitivity in the previous lesson about interprocedural analysis. Alias analysis can be made very interprocedural. That is, it absolutely has to do with lots of interactions between functions. So it often makes sense to bring in some kind of context sensitivity, like calling context, in order to make your alias analysis more precise. To show what I mean, let's bring back that little strcpy-like function that I wrote for you at the very beginning that sort of works like the strcpy function for C. Now imagine that we have two different calls to strcpy from a foo function and a bar function. And in one case, you're calling it with exactly the same pointer, that is, we're just doing strcpy of A and A. In some cases, we are allocating a new thing and passing it into strcpy, so these two things cannot possibly alias. A straightforward alias analysis that does not try to use interprocedural information, does not try to use calling context, will have to say that these two things may alias, and therefore this function does something quite odd rather than doing a proper string copy. On the other hand, if we introduce just a little bit of calling context, that is, if we introduce awareness of just the one function that called the string copy function, we can conclude that it is definitely the case that these two things alias in the context of foo and must not alias in the context of bar. And this is much more useful. Of course, as with any context-sensitive interprocedural analysis, there is a really sharp trade-off here between the precision and the cost. By precision here, for alias analysis, what I mean is it's the fraction, it's like the proportion of queries, of alias analysis pair queries that you can answer as either must alias or must not alias. And they don't have to go into that uncertain middle of the diagram I showed you before. Adding context makes alias analysis more precise, but of course, it also makes it way more costly. So at some point, there are diminishing returns to the additional precision you get at the cost of spending a lot more time analyzing your program. In general, having a scalable, that is efficient alias analysis that can analyze very large programs, where at the same time it is very precise, is a huge open research problem. I really can't emphasize this enough. There's like a whole research community out there about making good alias analyses that are both fast and precise. There's a huge body of research out there. I've left a couple of links into especially a really great tutorial by some people that have worked on alias analysis to give you an idea of the gigantic breadth of research that is there for just this one kind of analysis. And it's so important because, as we saw at the very beginning of the lesson, doing a good job with alias analysis is key to getting anything done that transforms programs that manipulate pointers. So any optimization you would like to do that has to do with memory has to rely on an alias analysis first before it can really do its work. And that's why it's so central in compiler optimization research.